So we are on balancing equations. I think we did this one yesterday, but I wanted to restart. So yesterday's class actually went into balancing equations after we did, is it balanced or not? Which you're always, basically when you're doing balancing, you're continually asking yourself, is it balanced or not? No, it's not, therefore I have to do something. Moving it on to the next step. So yesterday we did this one, but in order for us to have a presentation that's, starts with balancing, I thought we'd just take a backtrack just for a minute and re-review this example, example 6.3, that asks us to balance this equation. When you learn how to balance equations, you're going to look at something like this and go, this is a piece of cake. Why? Well, the first thing that's going to give you a hint is you have, on the reactant side, you have reactants that are in their elemental forms, right? These are homonuclear diatomics, so you're going to find them as molecules, which means because all I have are elements or homonuclear diatomics, I've got freedom to throw coefficients in front of that thing and not mess up any other part of that side of the reaction arrow, okay? It's not as if I add hydrogens over there that I've got to add it in 3 or 4 different places over here. It's just one place to increase coefficients. So that'll be more valuable to you later on, and you'll maybe review this lesson and go, oh yeah, look at that thing. This is a gimme. This is easy because all I have to do is throw coefficients up here and it doesn't affect anything but one atom, one element in the whole process. So let's go ahead and look at the elements that we're going to be considering. Again, the process I've encouraged you to do is look from left to right and list them as you encounter them. So from over left to right, we're going to move this way and we're going to encounter nitrogen and hydrogen and nothing else. And let's see if we have nitrogen and hydrogen and nothing else on the product side. Nitrogen, hydrogen, nothing else. Good, we're counting for everything. And then we go through and actually do the counts. So for nitrogen, on the reactant side, what are we looking at? Okay, I'd like to encourage you to say I have one set of 2. Now, I don't always put 1 times 2 because 1 times anything is itself and I don't want to mess up the screen, but I'm going to say it that way, at least for a while until it's comfortable to you. I have one set of 2. The sets of is the coefficient. How many in each set is the subscript? Okay, so for nitrogen, I have one set of 2, which is 2. And for hydrogen, I have one set of 2, which is 2. Now going over to the products. Nitrogen, what do I have? One set of 1. Okay, one set of 1 is 1. And for hydrogen, one set of 3, which is 3. Good. So we'll say one set of for a while. Eventually we'll be like, do I have to say one set of or can I just go 3? But get process in your mind right now. So what I encourage you to do now is look at those places where you have not used up all of the reactants. Where could you make more product? Or where do you have to make more product to use up all your reactants? So wherever nitrogen is used, right? You have one extra nitrogen left over from your reactants. You've got to use it up. We're going to use it up. You're going to increase the coefficient of something on the product side that involves nitrogen. Now this is easy because there's only one product. So you only have one coefficient on the product side that you can mess with. You've got to increase it. Increasing it to use up 2 would mean I need to increase the coefficient of ammonia to 2, right? So when we increase the coefficient to 2, we've messed up a coefficient on the product side, so we have to go ahead and recompute the counts for all products. And again, later on, you won't do it for all products, but for now, just for process, better to do a little bit extra work and get it right than to assume that you can just do it on the fly and ball it up in a big ball of fire, right? We're not going to do that right away. Let's start with products then. Looking at nitrogen. How many nitrogens do I have up here in this reaction equation? 2 sets of 1, which is 2. And hydrogen? 2 sets of 3, which is 6. Okay? 2 sets of 3, which is 6. Ask the question, where have I not used up my reactants? According to this, I've used them all up, right? I had 2 and I've used 2. I had 2 and I used 6. How'd you do that? Wait a minute, I used more than I had. So I need to request more stuff, right? I wished I had more reactant because then I could actually make it. Okay, ask for it. What do you want more of? You want more of the hydrogen, right? You need 4 more for a total of 6. How do you get 6 hydrogens. You look over here, and the only place it's available to you is in sets of 2. How do you get 6 from sets of 2? Right, you take 3 sets. So I'll take 3 sets of hydrogen. Since I messed up or I changed the coefficient on one of my reactants, then I'm recalculate my counts for all my reactants. So again, from left to right, looking for nitrogen. How much nitrogen do I have in the reactants? 1 set of 2. And hydrogen? 3 sets of 2, which is 6. So technically, this should have been 3 times 2 equals 6. Okay, sometimes I cut right to the answer, too, because it's kind of like when you say 1 plus 1, oh, wait, let me write that down before I forget it, and then solve it. Certain problems, you write it down. Certain problems, the answer is right there for you. So, but for process, I'd like you to write 3 times 2 equals 6, because I have 3 sets at 2 per set, which is a total of 6 atoms. Now I ask the question, is it balanced? It is, because my numbers match. My reactant side matches my product side. And what I didn't mention yesterday that you need to do next is look at your coefficients. The coefficients are 1, 3, and 2, and ask yourself, do they have a common factor? The only common factors they have is 1. If the only common factor is 1, we're good. This is the answer. If, hopefully you see, if the coefficients were 2, 6, and 4, you would say, oh, wait a minute, the greatest common factor there is 2. I can divide them all by 2. And you would get 1, 3, and 2. Okay? Balance the following. I think this is where the bell went off yesterday. So, let's go ahead and walk me through it. What are we going to look at first? What are we going to ask? Let's find out what the elements are, okay? What is the first element we encounter? Carbon. Second element? Hydrogen. And the third? Are there any others on the reactant side? No? Now look to the product side. We have carbon in 1, hydrogen in 1 of them, and oxygen in both of them. Are there any more or any less? No. The same elements are on both sides. You know, and if you miss that somewhere, when you eventually do your atom counts, you're going to find out, wait a minute, how did I get sodium on the right side? There's no sodium on the left side. The whole thing is wrong. It's impossible. I can't create sodium out of nothing. I need sodium in the reactants in order to have sodium in the products, and vice versa. It's got to be on both sides. Because again, we're not creating or destroying any elements. What we're creating or destroying are molecules, which are structures, not the elements themselves. We're not creating building blocks. We're creating things out of the building blocks. Okay. So we've identified all the elements. Next we look at maybe we should just like start a row and each person gets the next question. Okay, then participate a little bit. Okay, because the only way that's not going to happen, and if nobody speaks in 3 seconds, it becomes your question. Okay, so everybody throws you under the bus by nobody's going to talk. So what do we look at next? The atom counts, right? And the first place we're going to count them up is in the reactants. The reactants. Let's count them up. Carbon, 1 set of 3. Hydrogen, 1 set of 8. Oxygen, 1 set of 2. Okay. Now go to the product side. Carbon. On the products we have, for carbon, 1 set of 1. Hydrogens, 1 set of 2. Oxygens, correct, 1 set of 2 and 1 set of 1 for a total of 3. Oxygen is in both molecules. 1 set of 2 plus 1 set of 1. The ones are always implied. Okay? So is it balanced? Yes or no? No, it's not balanced. We need to start working the puzzle to solve it. I'm going to ask myself, okay, where have I not used up all my reactants? Just pick one of them. Don't pick, there's more than that here, right? We haven't used up all the carbon. We haven't used up all the hydrogen. We've used up too much oxygen. So let's start with what haven't we used up enough of? I tend to just start from the top, okay? We haven't, and look for look for elemental forms, either as the element symbol or a homonuclear diatomic, and save them for last. So if you have an option between two of them, save the homonuclear diatomics and the elements for last, because they're the easy cleanup at the end. All right. I'm going to suggest, excuse me, back up just for quick. I'm going to suggest that what we need to do is use up 2 more carbons. Just start from the top. We need to use up 2 more carbons somewhere. And the nice thing is carbon only appears 1 time in the products. So if I want to use up 3 and I'm currently using up 1, how can I actually use up all 3? Okay, so suggested 3. 3 becomes what? The coefficient of the carbon dioxide. Okay, it's kind of like a number means nothing without its units. Okay, we're going to solve it by 3 what? We're going to convert it to 3 carbon dioxides. We know we have to make at least 1 of each of them, otherwise they wouldn't appear at all, right? But we need to make 3 of them. Why? Because we had 3 carbons and we need to use it up, and that's the only place we can use it up at. But because we changed the coefficient on the product side, we're going to go through and do the counts again for all the products. So, elemental counts on the product side. How many carbons are currently being used for production? Say we see 3 of them, 3 sets of 1. Hydrogen, 1 set of 2, and oxygen. 3 sets of 2 and 1 set of 1 for a total of 7. Okay. Again, where have we not used up all of our reactants? Hydrogen, okay. We need to use up more hydrogen. We had 8, but we need to use up 8. We've only used up 2. So we need to use up 6 more. How are we going to use up more hydrogen? We look to the product side and we find, where does hydrogen occur? Again, luckily for us, it only occurs in 1 place. Because it gets all confusing when it happens in more than 1 place. Because then you're messing up 2 elemental counts, or 2 molecules, which is going to mess up the counts, right? It's going to mess up the counts of other elements. In here, if the only place it occurs is in the water, and I change the coefficient on water, I'm only messing up the hydrogen and the oxygen counts. If I was trying to change the number of oxygen over here, I might have to change both the carbon dioxide and the water coefficients. You see that? But since it's only hydrogen, and hydrogen only affects the water molecules, then it's much simpler. All right, so we've balanced the carbon. We're now looking at hydrogen. Hydrogen has to balance it as well. We have 8. We've used 2. In order to use up 8, what must we do? Change the coefficient of water to 4. Because if I use up 4 sets of 2, I've used up 8, and I have 8. So I'll do that. Boom, there's my 4 sets of 2 for hydrogen. But since it's a product, I'm going to wipe the product side clean and redo the count. So, counting up products for carbon, how much carbon do we have? 3 sets of 1. Good. For hydrogen, how much hydrogen do we have in the product side? 4 sets of 2, that makes 8. And oxygen. Very good. 3 sets of 2 and 4 sets of 1 for a total of 10. 3 sets of 2 is 6 and 4 sets of 1 is 4, obviously, and that adds to be 10. So I have 3, 8, and 2, and I have 3, 8, and 10. Is it balanced? No, it's not balanced. And the terminology is, it's not balanced with respect to oxygen. And remember, if it's not balanced with respect to any part, it's unbalanced in its whole. So I would say up here, hey, I've got an equation, but it's unbalanced with respect to oxygen, because the oxygen counts don't match. So I have to make them match. And here's the deal. Since we saved oxygen for the end, and oxygen appears in the reactants in its elemental form as a homonuclear diatomic, we just throw the coefficient in there, and it doesn't mess up anything else on the reactant side. It only affects that 1 molecule. Okay? So we say that we've used up 10, but we only have 2. So how do we get 10 on the reactant side? Go ahead, Zach.
5 for the oxygen.
Ask for 5 oxygens. So you get to request things, and then say, well, if you get what you requested, what's it going to look like? We changed one of the reactant coefficients, therefore we're going to recount all the reactants. Reactants with respect to carbon, how many? 1 set of 3. Hydrogens? 1 set of 8. And oxygen? 5 sets of 2, which is 10. Is this reaction equation balanced? Yes, it's balanced. With respect to carbon, hydrogen, and oxygen. With respect to every element involved, it's balanced, therefore the whole thing is balanced. Now, what I didn't encourage you to do yesterday, I'd like you to do today, is go back and look at the coefficients of the balanced reaction equation. 1, 5, 3, and 4. What is the greatest common factor? 1. We're done. Hypothetically, if it was 2, 10, 6, and 8, the greatest common factor would be 2. We'd divide everything by 2, and you would end up with 1, 5, 3, and 4. See, what this is giving you right now is the simplest whole number ratio that forms a recipe. It forms a recipe for what you want to make. You're trying to make carbon dioxide and water. To make carbon dioxide and water, what do you need? You need C3H8 and O2. How much do you need? Because it's not enough to say, I'm making something. What do you need? Flour, eggs, and milk. So what do? Pour the whole box of flour in, and then the whole gallon of milk in, and the whole dozen eggs in? No, you need a little more information than that. Certain amount of flour, in proportion to a certain amount of milk, in proportion to a certain amount of eggs. And if you get the proportion right, you get the right thing out of the oven. But if you get the proportion wrong, in baking, it messes up the product. In chemistry, you're still going to get the right product, but you're going to have extra ingredients sitting on the side. Like you put too much in. You don't need this. Or if you want to use this up, you need more of something else to use it up. So you can make a double batch. That's what it is when you go through and you had, like, for example, 2, 10, 6, and 8. That would be the recipe for a double batch. Why? Because I could reduce that recipe in half to be 1, 5, 3, and 8, and 4. Okay? But the smallest batch I can make using whole numbers is this right here. Now, there is a method to solve it by going to fractional coefficients. That does happen sometimes, and we'll address how to fix that later on. Well, basically, here's the deal. If you end up with a fractional coefficient, like if I decide to take half of an O2 and it was 5.5, I still have to make sure that I have whole number integers, whole integers for my coefficients. So if any one of my coefficients, for example, was a half, I've got to make it at least a 1. So I'm going to multiply everything by what's ever needed to make the fractional one a whole number. And ideally, to make every one of them a whole number. Okay? All right, so this is the balanced reaction equation for this production of carbon dioxide and water. So everybody good on this? You kind of got the process down now? Okay? The same process you're going to be using every time you balance the reaction equations for weeks on end. Okay? So make sure you get the process down mentally now. Because we're going to do the same thing now with, this is on your own 6.8. It's the reaction to produce water from hydrogen and oxygen. So I need, should I get the beach ball out? Yeah, I think I should, because otherwise I have the same 2 or 3 people give me hand signals and nobody talking. And we need to get a little bit more responsive than that. So, oh, sorry, Derek. Wasn't necessarily aiming for you, but because of the projector, you get the ball first. So pass and answer, okay? There you go. What am I going to do?
Name your elements.
What are they?
Hydrogen, oxygen.
Anything else? Are they present on both sides?
Yep.
Is there anything else? Nothing missing? Not too much, not too little? Okay. Pass. Just go ahead and... What do we do next, ma'am? Okay, help me out then. What are we going to put down?
So for the reactants, it's for hydrogen 1 set of 2 and oxygen 1 set of 2.
Okay, 1 set of 2 and 1 set of 2. Next.
On the product side, hydrogen has 1 set of 2 and oxygen has 1 set of 1.
Okay, 1 set of 2 and 1 set of 1. So where are we out of balance? Where are we not balanced with respect to? So what are we going to do? What do we need to do? Add coefficients. Adding the coefficient is to use up more of the reactant, right? That's kind of what we're getting at. We can make more stuff. We want to make more stuff. We've got to use up the extra stuff that was given to us somehow. So we're going to increase our use of oxygen. Now the nice thing is on the product side, there's only one molecule. So there's only one place to look. So how are we going to fix that? Okay, so we're going to say we want to produce 2 molecules of water. But that is a change of a coefficient on the product side, so we need to recompute the counts for all the products. So what are those counts?
You got 4 hydrogen.
Okay, so we've got 2 sets of 2, 2 sets of 2, which is 4, and
You got 2 sets of 1 for oxygen.
2 sets of 1, which is 2. Okay. Is it balanced? It's not balanced. Okay, next. You want to hand off and then we'll... It's not balanced with respect to...
Oxygen.
Not balanced with respect to oxygen, so... Or, excuse me, with hydrogen, right. Not balanced with respect to hydrogen. We used up too much hydrogen, right? So we used up more hydrogen than we have. So let's try to make this true. What do we need to do?
Put 2 with the oxygen.
Okay, we're short. This shows me that we're short with respect to hydrogen, right? We're saying that we used 4, but we only have 2. We used more than we actually have. So let's request more stuff so we can actually make what we said, right? So we're unbalanced with respect to hydrogen, and we've got too few reactants of hydrogen. So where do we need to add the coefficient?
You put a 2 for the H on the reactant.
Right over here. So we're going to add the 2 to make it 2H2 plus O2. Now we've changed the coefficient on the reactant side, so we wipe that clean and do the count again. So, ma'am?
Hydrogen has 4.
Because it's, I know it's tedious, but let's say it's 2 sets of 2, which is 4. Okay. And oxygen?
Has
1 set of 2, which is 2. Is it balanced? Okay, it's balanced. We're done. Is it?
We gotta do the thing.
We do?
The
Okay, what's the greatest common factor?
Dang, I didn't do that.
1. Greatest common factor is 1. We're done. Right? For those of you that thought we weren't done, why weren't we done?
I was looking at the numbers on the reactants and products below the equation. Got confused.
Okay. But is it balanced? Am I wrong? Or, I mean, it's balanced, right?
Yeah.
It's balanced. The only thing we didn't formally ask was what's the greatest common factor, because I saw that there was a 1. And if there's any implied 1s as coefficients, you're done. So, another equation on your own, 6.9. Now the questions are a little bit longer than this. I think this one was a word problem, but it basically reduces down to this. Calcium and oxygen and carbon produce calcium carbonate. Again, if you're balancing equations, you should look at this and go, hoo-hoo, this is going to be so easy. Why? Look at my reactants. What do I have as reactants? Every single one of them is in its elemental form. I've got elemental calcium, homonuclear diatomic oxygen, and elemental carbon. If I change any coefficients over here, the only thing it's going to affect is that element. This is like the jackpot in balancing. This is going to be so easy. So let's go ahead and formally do it. First portion is to look at the elements. What are the elements involved?
calcium, oxygen, carbon.
Right, calcium, oxygen, and carbon. Calcium, oxygen, carbon. Calcium, oxygen, carbon. Nothing more, nothing less. Those are the elements. Next, we're going to do the counts of the reactants. Those counts are
1 set of 1, 1 set of 2, and 1 set of 1.
correct. 1 set of 1, 1 set of 2, and 1 set of 1. Done with reactants, we go over to the products now. pass quick and respond with the product counts as
One set of one.
one set of one?
One set of one.
No.
One.
Oxygens.
One
Right?
set of three.
One set of three and
One set.
no. Here, let me back up again. Let's start.
Oh, okay. I was looking at wrong.
Okay, so for calcium, we're looking at the product side, everything to the right of the reaction arrow, over here. The calcium count is one set of one, which is one. Then we're going to look at the oxygen count. The oxygen is here. It is one set of three, which is three. And then carbon, one set of one. Remember, there's no such thing as the element capital C, capital O, subscript 3. Okay? Capital C, lowercase o is cobalt. Capital C, capital O is a carbon and an oxygen. Right? Okay. Like I said yesterday, I only say this because there's several of you that made this error on the last exam a couple different times. You did your molecular geometry, but your central atom was represented by 2 capital letters, which meant you made up an element because we don't write it that way. That's 2 elements if they're both capital in their atomic symbols. Okay, so next question we're going to ask ourselves is what? Is it balanced? And the response is no. And what is it not balanced with respect to? Not balanced with respect to oxygen. Good. So, one last question for you. What are we going to do? It's got to be something to do with oxygen, right? And because we're saying that we used more than we had to start with, we need more to start with. So we're going to change the coefficient where? Right, we need to start by changing it over where we get what we started with. We started with this and we ended with this. This is saying we ended with more than we started with. We need to bump the number up over here. We need to bump the number of oxygen up over here. What are we going to change it to? Eventually, let's just keep simple process now. Well, let's start it with 2. Let's go simple. You're right. If you saw that, if you can see the end already, that's good. You're looking at that 3D poster that's looking like just a bunch of squiggly lines, and suddenly it comes out to you and you see the image. Okay, that's kind of what learning is like, and this stuff is like. You're going to start to see the end, but for right now, I want to just keep walking you through the process, because if you're struggling with that image and it hasn't popped out at you yet, at least if you follow the process, you'll end up at the right place. Okay. So if this seems tedious, I apologize. But right now, we've changed a coefficient of a reactant, so we're going to recount all the reactants. We only changed 1 right now. Okay. So what is our new counts?
Calcium would be 1.
Say it the tedious way. 1 set of 1.
1 set of 1.
Okay. So 1 set of 1 oxygen. 2 sets of 2 to be 4. Good.
And carbon would be 1 set of 1.
Carbon's 1 of 1. Right. Is it balanced? Ma'am, what's it not balanced with respect to? Not balanced with respect to oxygen. Okay. So what are we going to do about it? We only have 1 product, so we only have 1 coefficient we can play with, right? So we might as well just walk it up. Let's walk it up. Let's go ahead and pass off. Who has not gone yet? Anyone? You guys kind of have a standard pattern you hand off to. Have this reciprocal agreement with one another, right? Oh, break the pattern. Okay. So, well, you're up. Now you need to pass it again already because she held on to it while she answered. So, ma'am, we were at the products. Let's do the counts. We've added the coefficient 2 in front of the calcium carbonate. Count them up. Calcium?
Okay,
2 sets of 1 for calcium. You did this one or the product last time, didn't you? Okay, let's do it again. Oxygen.
1 set of 3.
Try again.
Oh my gosh, 2 sets of 3.
Okay, so 2 sets of 3, which is 2 sets of 3, which is 6. Good. And carbon. 2 sets of 1 or 2. Is it balanced? No. What's it unbalanced with respect to?
Everything. Oh my gosh.
It's unbalanced across the board. Now, it might seem like you've messed it up because before we were unbalanced with respect to 2 elements, 2 parts. 2 elements. Now we're unbalanced with respect to all of them. But where is the unbalanced portion at? Where are we going to be tweaking next? Correct, the reactants. Why? Because in every case, we've said we've used up more calcium than we had, we've used up more oxygen than we had, we've used up more carbon than we had. So we're going to have to change all of our reactants. And guess what? They're all in elemental form, which means this is when you're really tempted to just fix them all. Because who's next? Pass? Okay. Good. Thank you for changing the pattern. What are we going to say? We used up 2 calcium, so we need to have 2 calcium. How do we get 2 calcium? Put a 2 in front of the calcium. What about oxygen? We used up 6. We only have 4. To have 6, we need to... Good. Change the coefficient of oxygen to a 3. Oh, and by the way, we're still unbalanced with regard to carbon. We say we used up 2, but we only have 1. We can fix that by putting a 2 in front of the carbon. Now, simplest question of the day. Elemental counts of calcium.
We got
2 sets of 1.
2 sets of 1.
Oxygen,
3 sets of 2.
which is
6.
6. And carbon?
1 set of 2.
Try again.
1 set of 2.
2 sets of 1.
2 sets of 1.
Okay, it's important. It's important.
1 set, oh. Okay.
I know 1 times 2 equals 2 times 1, but the process is this many sets of this many. That's the process I'm teaching you. So here it's 2 sets of 1, which is 2. And you ask yourself the question, is it balanced? Yes. Because you've held onto the beach ball, so you just keep answering questions until you get to hand it off, or you can just hold it. So, is it balanced? Oh, I'm sorry, I already asked the question.
Yes.
Is it balanced? It is balanced. Okay. Now, I'll switch the question down here and ask, are we done? Okay. What do we need to do? Are we done? Let's get group consensus. Are we done? Yeah, we're done. Why? Because there is no common no greatest common factor there. Or excuse me, rather, the greatest common factor is 1. There's nothing other than 1 that's a factor of every one of those coefficients. Of 2, 3, 2, and 2, the greatest common factor is 2. We're done. So what is this telling us? It's saying that if I have 2 molecules of solid calcium and I react it with 3 molecules of gaseous oxygen and 2 atoms of carbon, it will produce 2 calcium carbonate molecules with nothing left over. Okay? It will also produce this in any multiple of that. So 4 reacted with 6 and 4 will produce 4. It's just a double batch. If I take the coefficient and multiply it by 5, 10 and 15 and 10 produce 10. Multiply it by 13. 26 and 39 and 26 produce 26. A bazillion. 2 bazillion and 3 bazillion and 2 bazillion produce 2 bazillion. You see? It's a relational proportion. If you want to make a bazillion batches of it, you multiply everything by a bazillion. Okay? And if you make a bazillion batches, you're going to have 2 bazillion calcium chloride, calcium carbonates.
I understand.
You get it? What it does not mean, it does not mean that if you add 2 pounds and 3 pounds and 2 pounds, it produces 2 pounds. That's not what it means. Okay? If you add 2 grams and 3 grams and 2 grams, it produces 2 grams. That's not what it means. Because it's not talking about the mass. Unless we're talking about gases, it's not talking about the gases. And we'll get in Guy Lassac's rule later on. But what we're talking about is the count of the building blocks. And they are in a relationship with one another. And you can make batches. And you can make partial batches and whole batches. But you need to know what it takes to make one batch first. And this is the perfect recipe for one batch. The balanced reaction equation. Now, I haven't used my notes today, so hopefully we're almost done. No, we've got one more equation to balance, and we've got like 4 minutes to do it. So let's do it. On your own, 610. And we're doing it on our own as a group. So, okay. Balance the following equation. Ma'am, what are we going to do first? Identify, right? Identify the elements. So they are non-metal, non-metal, non-metal. No, I'm kidding. Doing the classification, not the identification. Okay, so the elements are carbon, hydrogen, oxygen. Left side CHO, right side CHO, nothing else. Okay, so we're dealing with CHO again. It's another. Okay, we deal with CHO all the time, so just get used to seeing CHO. In fact, I say count from left to right, but sometimes you'll see carbon and oxygen and hydrogen, and people will start writing CHO because organic chemistry. All right. So let's do the reactant count next.
1 set of 5, 1 set of 12, and 1 set of 2.
Right. Product side, somebody else?
One set of one.
One set of one,
One set of two.
one set of two, good, and
And then one set of two and one set of one.
one set of two and one set of one for a total of 3. Right. Next person, is it balanced? No, it's not balanced with respect to everything. Okay, next person. Give me a fix. Okay, so you're doing that because you want to use up all your carbon, right? You said, I want to use up, I've got excess carbon in the reaction side, let's use it all up. The only place carbon is over there is in carbon dioxide. You had 5, each molecule uses 1, so you decided to put a 5 in front of it. That's all the logic you went through in your mind. You just may not realize that, but that's what you did. So that's a good answer. But because you changed the coefficient, of a product, we're going to recount all the products. So what is that count? Okay, 5 sets of 1. Hydrogen is 1 set of 2, and
Oxygen is 5 sets of 2 and 1 set of 1.
5 of 2 and 1 of 1, which is 11. Okay, next person. Okay, Zach, I think he's passing around to you. Other side? Huh? So, what are we going to do? So they're not balanced. We're balanced with respect to carbon, but not with the other two. We first try to use up excess. We say we had 12, but we only used 2 hydrogens. So what are we going to do? Okay. Now, hear what he said. We're going to add. Okay. That's a different way of thinking about it than we've been doing it. It will work, but you might mess up your math. I'm just warning you right now. If you say we will add, you'll look at this and say, well, how many do you have to add? 10. Good. You add 10. So if you're adding 10, you need to go up there to your, adding 10 would be what? No, you cannot change a subscript. If you ever change a subscript, you are wrong. You have to change the coefficient. Okay? Here's what the common error is. People say, I need 10 more. 10 more, they're in sets of 2. I need 5 more, and they'll stick a 5 in front of that. You've just destroyed 2 hydrogens because there was a 1. You're not adding 5 to 0, you're adding 5 to 1, which makes it 6. The way I've been teaching you to look at it is, I used up 2, I had 12. How do I use up 12? 6 sets of 2. Okay? Which is the same, you're going to get the same answer if you do it right, but your way requires that you add to what's there, and if there's an implied 1, many times people would have put a 5 there and forget that they're adding 5 to 1, which makes it 6. So we go through the counts. There's 5, 12, and 16. We need more what? We need more oxygen. We need to have 16 total. And to have 16 total, we need 8 sets of 2. Okay? 8 sets of 2. We go through the counts now. There's 1 set of 5. There's 1 set of 12. And there are 8 sets of 2, which is 16. And the reaction equation is balanced.